My name is Antoine Moulin. I'm a PhD student supervised by Antoine, and I'm excited to share the work we've been doing in reinforcement learning theory. Reinforcement learning, or RL for short, is a type of machine learning that focuses on learning through interaction with an environment. The agent receives feedback in the form of a reward signal and learns to take actions that maximize this reward. In this video, I focus on the online RL setting. The data is gathered in a sequential order as the agent interacts with the environment, and it can only learn from this single stream of experience. Unlike supervised learning, where data is generated from a fixed unknown distribution, in RL, the data distribution depends on the behavior of the agent. Therefore, the agent does not just have to maximize its reward based on its current knowledge, but also has to collect information about how the environment works. Such a trade-off is at the core of online RL. Now, the goal is simple. We want to find a policy pi that gets as close as possible to the maximum sum of rewards one can hope to achieve, here denoted as V star. The expected sum of rewards pi can get is denoted as V pi and is known to satisfy Bellman's equation. V star also satisfies a similar equation named the optimal Bellman equation. And to solve this problem, the first algorithm one studies is value iteration, and it goes as follows. Because the operator induced by the optimal Bellman equation is a contraction, Banach's fixed point theorem tells us that if we keep iterating it, we will converge to its unique fixed point, which happens to be the optimal value function. However, a drawback is that such an algorithm requires the knowledge of the transition probabilities. So we're going to apply a first modification to this algorithm. We replaced the true transitions by an estimator, and because we are in the online setting and we need to explore, we add an exploration bonus. Roughly speaking, we can think of adding such a bonus as a way to plan in the best statistically plausible world. This is called the principle of optimism in the face of uncertainty. Now, there is another drawback. In general, for instance, when we use a least squares estimate, we have no guarantee that this approximate Bellman operator converges to anything. This leads us to our second modification. We show that if we use regularization and approximate the maximum and argmaximum as shown on the slide, we can achieve convergence on average. In particular, we show that over k epochs, the sum of the suboptimality gaps of the iterates our algorithm computes is bounded by two simple terms. The first term is just the sum of the exploration bonuses along the agent's trajectory. It is a standard quantity and in several settings can be shown to scale as quote of k. The second term is the optimization error induced by the regularization. With a proper fine-tuning, this scales as square of k2. This means that the average of the suboptimality gaps converges to 0. The main advantages of this algorithm are that we can now go beyond finite horizon MDPs, and second, we avoid assumptions like contractivity or monotonicity as required by previous works. And beyond the advantages that I just mentioned, there are obvious future directions. First, how can we extend this result to a richer structural assumption, such as linear MDPs? And second, how can we extend this to the harder yet more interesting setting of average reward MDPs? Thank you for watching.